This is RD Sharma Solution Class 12, Chapter 7, and we are doing VSAQ, very short answer question, from Chapter number 7, Adjoint and Inverse of a Matrix. Write the adjoint of the matrix A. So there is a shortcut method. I'll just tell you how to do that. But before that, the proper method, the way in which we do this adjoint is by making a cofactor matrix. So when you make a cofactor matrix, this is true for 2 by 2 matrix, 3 by 3 matrix, and so on. So when you write this 3, 4, 7 minus 2, it is minus 3. So I'll just change it. So there are 2 rows and 2 columns here. So we call it as C11, C12, C21, C22. This subscript shows the rows and column. So C11 is minus 1 to the power 1 plus 1. I'll tell you what to write there. Then minus 1 to the power 1 plus 2 for C12. For C21, it's minus 1 to the power, again 1 plus 2 or 2 plus 1. And please remember C22 minus 1 to the power 2 plus 2. What I'm trying to tell you for remembering is minus 1 to the power even is always 1, minus 1 to the power odd is always negative 1. So C11 we are taking C11, that is just hide C11 row and column and write the value, that is minus 2. C12 hide the column and row for C12, 7 will come. And then we have C21, hide the column and row for this C21, you get 4. And leave the column for minus 2, row and column, that is going to be minus 3, that is negative 3. I'll just change it. So negative 3 it is. So this is negative 3. Okay. Now this, as I said, minus 1 to the power odd is going to be negative. Minus 1 to the power even is always positive. So minus 1 to the power 3, minus 1 to the power 3. There are 2 places, so it will be negative. Here it will be positive. It is negative, and this is also positive. Okay. So the sign of C12 and C21 will change. The rest will be same. Minus 2 here. 7 will be negative 7. This is going to be negative 4. And this is going to be negative 3. Okay. So let us write this cofactor matrix. As I said, cofactor matrix, you have to write this as minus 2. In place of C11, in place of C12, replace it by the value minus 7, then minus 4, minus 3. Okay, this is just a cofactor matrix. In order to find out the adjoint, we have to take the transpose, row to column, column to row. So minus 2, minus 7, the row was made as column, minus 4, minus 3 was a row, and we made it as a column. So this is the final answer. Okay, now I'll tell you the shortcut method. Shortcut is negative 3 and negative 2. These diagonal values need to be exchanged in place of, or in case of 2 by 2 matrix. So I'm just doing it directly. Minus 2 here, minus 3 here. So we have exchanged the value of minus 2, minus 3, and 7 and 4. Keep it there, but just change the sign. So minus 7, minus 4. Right? So the same thing has come. These are the ways. Now if A is a square matrix such that A into adjoint A is equal to 5i. So A into adjoint A is equal to 5i, it is given, where I denotes the identity matrix of the same order. That is, again, we are talking about this same order. Then find the value of determinant of A. Okay. So here, we already seen in the exercise, in the properties, when we were discussing theory, we knew that A dot adjoint A is equal to determinant of A multiplied by the identity matrix. Okay. So what is 5 here? If you equate it, the determinant of A is equal to 5 here. Now if A is a square matrix of order 3 such that determinant of A is equal to 5, write the value of determinant of adjoint of A. So in any kind of square matrix, adjoint A, the determinant of this is equal to the determinant of A raised to the power n minus 1. So adjoint A, we have to find out. The determinant of A is already given to us, which is 5. And what is the order? That is going to be 3. So in place of n, you'll replace it by 3. 3 minus 1 is 2. So 5 square. That is going to be 25. Now if A is a square matrix of order 3 such that adjoint of A, determinant of adjoint of A is 64, find the determinant of A. So again we have the, the property and the relationship adjoint of A, determinant of adjoint of A is equal to determinant of A raised to the power n minus 1. This is 64 given already, and this is determinant of A, n is 3, so 3 minus 1 is 2. Okay, so we get determinant of A square is 64. You can write 64 as 8 square. 8 square is determinant of A whole square. That is simply equal to x square. You can write that determinant of A is equal to plus minus 8. It can be plus 8, it can be minus 8. If A is a non-singular square matrix such that determinant of A is equal to 10, find the determinant of A inverse. So all the properties we have already discussed in the theory. So I'll just give you this determinant of A when it is not equal to 0. Then what we will do? Determinant of A inverse is nothing but is equal to 1 by determinant of A. This we have to find out, 1 by determinant of A. So this is 1 by 10, and that is the answer. If A, B, C are 3 non-null square matrices of the same order. Non-null means matrix with all 0 values. These are of same order. Write the condition on A such that AB equals AC implies B equals C. So that means you are able to eliminate A. Then only B and C will come. You can cancel out A. How that is possible? I'll just show you how it is possible. See. So this is AB equals AC. Now both the sides will be multiplied by A inverse. I'll tell you what is the condition, but first let us multiply by A inverse. This A inverse A is going to be identity matrix. Even A into A inverse, A inverse into A is going to be identity matrix. So this is identity matrix. So identity matrix into B equals identity matrix into C. That is, anything multiplied by the identity matrix is going to be the same matrix. So B equals C. Now for that A inverse should exist. And what is the condition for A inverse to exist? When it is invertible. That is, determinant of A is not equal to 0. That is the actual scenario here. Okay. So determinant of A should not be equal to 0. If A is a non-singular square matrix such that A inverse equals this value, then find the A transpose and inverse. Now non-singularity is determinant of A is not equal to 0. So A transpose inverse is equal to A inverse transpose. So A, you take the transpose, take the inverse, and that is equal to A inverse, and then we have the transpose. So they both are same thing, right? So A transpose, we already know that A inverse is already given here. So A inverse is given here, so we can just take this value and we can take the, so I'm just transposing it. So 5, 3 minus 2 minus 1, A inverse transpose, A transpose inverse is this answer. Now adjoint A is equal to adjoint B. No, adjoint A and adjoint B is given. We have to find out adjoint of AB. So adjoint of AB, the expression is like this. Adjoint of AB is nothing but, see, adjoint of B. Please remember this. Adjoint of B multiplied by adjoint of A. So B will come first and then comes the adjoint of A. Okay. So adjoint of B is given 1 minus 2 minus 3, 1. Adjoint of A is 2, 3, 4 minus 1. So let us multiply this. 1 into 2 minus 4 to the 8. It's not 6, it's 8. I'll just change it. Now 3 and minus plus 2. So this already done. First row with both the columns. And now the second row with both the columns. So minus 3 into 2 plus 4 into 1. Next one is minus 3 into 3 plus 1 into minus 1. Okay, what do you get? Here you get 2 minus 8. I'll just change it. It is going to be minus 6. So minus 6, 5 minus 2 minus 10. That is going to be your final answer, right? So this, as I said, I'll just change it. It's minus 6. This is your final. But please remember, it's adjoint AB is adjoint B into adjoint A. If A is a symmetric matrix, write whether A transpose is symmetric or skew symmetric. So A is symmetric matrix. Symmetric means A transpose is equal to A. So when A transpose is equal to A, then A transpose is also symmetric. Because skew symmetric simply means A transpose is equal to negative A. That is not the case here. So A transpose is A for any symmetric matrix. A transpose equals to A. So by this definition, A transpose is also symmetric. Otherwise, if it is negative A, it will become the skew symmetric, which is not the case here, right? So see it here, it's symmetric only. A transpose is equal to A. If A is a square matrix of order 3 such that determinant of A is equal to 2, then write the value of adjoint of A. Again, we have a relationship here. Again, we have an inequality here, equation here. So in any square matrix, the determinant of A, we are interested in adjoint of A. That is, first we have to find out the adjoint of A, then we have to find the adjoint of that resultant matrix. So adjoint of A is simply determinant of A, and then to the power of n minus 2, and then we have A here. This is the relationship you have to follow, okay? So what do you get? So determinant of A is already given as 2, raised to the power n minus 2, n is your 3, so 3 minus 2 is 1, so 2 twice of A, that will be the answer. If A is a square matrix of order 3 such that determinant of A is 3, then write the value of adjoint of A. So we have just seen this is adjoint of A. So this is adjoint of A we just saw. But the question is asking about adjoint of A determinant. So it has another relationship which I am going to tell you just now. It's adjoint of A. When we find the determinant, it's going to be determinant of A to the power of n minus 2 into A. But here we have the determinant of this. So when you have the determinant of this, adjoint of A, determinant of this is determinant of A raised to the power n minus 1 whole square. I hope you got the idea. So that determinant of A to the power n minus 1 whole square. What is determinant of A? It's 3. What is n? 3. 3 minus 1 is? That is going to be 2. So 2 square it is. So determine this 3 to the power 4. 3 into 3, 3 into 3, that is 9 9s are 81. 81 will be your answer. Okay. If A is a square matrix of order 3 such that adjoint of 2A. So square matrix means the rows and columns are same. So this is order 3. So 3 rows and 3 columns. And this is given that adjoint of twice of A is equal to K into the adjoint of A, then we have to write the value of K. Okay. So we already know by our previous discussion that this adjoint of 2A is given, but if this 2 is some lambda or some K, so adjoint of lambda into A is equal to the lambda or K to the power n minus 1. And then adjoint A. Okay, in this case, we will put lambda equals 2, and in place of n, we are going to replace it by 3. And of course, we have the lambda raised n minus 1 followed by adjoint of A. Okay, so adjoint, then this I am writing as 2A, lambda we are writing 2 again, and n is 3, 3 minus 1 is 2. So adjoint of A. Okay. So 2 square is 4, adjoint of A, and then we have on the left hand side adjoint of twice of A. Now please, in the question, please witness that adjoint of twice A is given as is equal to K adjoint of A. So why not to equate these two? Let us equate it, because this is already given in the question. So I'm just equating it here, adjoint, or writing it here so that you can see the equality. Adjoint of 2A is equal to K into adjoint of A. Now from these two equations, K is equal to 4, K is equivalent to 4. So you can just write K equals 4. If A is a square matrix, then write the matrix adjoint A transpose minus adjoint A transpose. Okay. So let me tell you, there is when we are discussing the theory, I told you that the determinant of A when it is not equal to 0, that means we have the non-singular matrix. So the adjoint of A transpose, that is, you take the A transpose and then find out the adjoint, or you can find out the adjoint A and then you can transpose. Both of it are equal. When you take it on the left hand side, it is going to be not 0 but null matrix, because these two are actually matrix. So adjoint of A transpose minus adjoint of A whole transpose is equal to null matrix, because these all are matrix. So the answer will be null matrix here. Null matrix is all about zeros. There is nothing in the matrix. All values are 0. Null matrix. If A be, let A be a 3 by 3 square matrix such that A into adjoint A is twice of identity matrix 2i, what is the value of determinant of adjoint A where I is the identity matrix? So this question, type of question we have already done. And when we know that the matrix A of order n, the A multiplied or A dot adjoint of A is equal to determinant of A, and then I n subscript is showing that what is the order of the matrix. It can be 3, it can be 2. In this case, it will be 3. In this case. Okay. So adjoint A determinant we have to find out. But we know the value of this. From this we can relate to the question. The question is saying A into adjoint A is equal to twice of I. Since we already know this equation, we can equate these two equations, one in the question and one which we already know. A dot adjoint A is equal to determinant of A into In. So I am writing now what is given. A into adjoint A is equal to twice of I. Now if you see here, we equate a determinant of A is equal to 2. This is already given. So now determinant of A is 2. Now we already know that the determinant of adjoint A is nothing but determinant of A raised to the power n minus 1. We have already done a question like this in this exercise. So determinant of A is 2. Order is 3. So 2 raised 3 minus 1, that is 2 square, is 4. If A is a non-singular symmetric matrix, write whether A inverse is symmetric or skew symmetric. Okay. We have already seen a question like this. Again, let us revisit this. Now, A is invertible only when the determinant of A is not equal to 0. So, A inverse only exists when the determinant of A is not equal to 0. Okay, and this question is saying that A is a non-singular symmetric matrix. What does symmetric matrix means? A transpose will be original matrix A. That is symmetric matrix. If it would have been skew symmetric means A transpose is negative of A, right? So A inverse transpose is equal to A transpose inverse. This already we know. This is a property. A inverse transpose is AT transpose. So AT is A. So let us write A here. So this is going to be, I'm writing A transpose as A. So A inverse. So when you take the transpose of A inverse and you get in return A inverse only, that means this A inverse is nothing but the skew symmetric. If it would have been a skew symmetric, that is A inverse transpose will be equal to minus of A in A inverse. But since we get this in an equation, this is symmetric matrix. Now A is given this matrix and also A into adjoint A. I'll just tell you what this exactly, the question is. I'll just write it because there is a slight change here. I'll just write it. So first let us concentrate on this A. A is, we are interested in finding out K. But let us go with A, and we need to find out the determinant of A just to show that A inverse exists. Then only we will be able to solve this. Because eventually we are going to find out we are going to multiply it with A inverse. So determinant of A is simply cos square minus sin square minus plus will be. So because there one is negative. So cos square plus sin square theta here. Okay. So this is going to be 1. Determinant of A is equal to 1. So since it is not equal to 0, we can easily say and safely say that this is showing us that A inverse exists. Now A inverse, we know the formula already. A inverse is adjoint of A and divided by determinant of A. This is a standard expression we know. Determinant of A is already 1, so we can just write A inverse is equal to adjoint of A. Now what we'll do here is, as I said, we need to tell that A inverse exists. Now we will multiply both sides by A. Determinant of A is 1, so we are just not taking that, one more defect. So A into adjoint A it is. So A into adjoint A, let me write it here as I just told you. It is A into adjoint A. This is like this. So we need to find out A into adjoint A. For that we need to multiply A on both the sides just to get what is required in the right hand side. So since this is available to us and A into adjoint A we want, so we'll multiply both sides by A. Now this right hand side we already got because already given it is K 0 0 K. On the left hand side A into A inverse is what? It is identity. It is identity matrix. So we can just write it as 1 0 0 1. The diagonal should be 1, others should be 0, and you just equate it K equals 1, K equals 1. So this is your K. If A is an invertible matrix such that this determinant of A inverse is equal to 2, find the value of a determinant of A. So the question we have already done, and the A inverse, if you take the determinant A inverse, it is going to be 1 by determinant of A. This is as simple as when the determinant of A exists, 2 inverse you can write it as 1 by 2. This is just like that. Because determinant A is all about value. Okay. So this the value is A, the determinant of A inverse is 2. So you can write it here, 1 by determinant A. The determinant of A will be, take 2 on the right hand side, it will be 1 by 2. This is your final answer. If A is a square matrix such that A into adjoint A is this matrix, this is basically a scalar matrix, you can take 5 out, that will be an identity matrix. So 5 into I it is. If you multiply 5 to the identity matrix, you will get this matrix. Then write the value of determinant of adjoint A. So A into adjoint A is already given in the question, and since we can just write it as 5 into I as I just suggested you, if you take 5 outside, it will be 1 1 1 in the diagonal, and that is essentially equal to the identity matrix. So determinant of A into, because A into adjoint of A is determinant of A into IN. We have just seen in the last questions, few questions we have done. So determinant of A into IN is equal to A into adjoint of A. So determinant of, now you can equate this, determinant of A into IN. So determinant of A is 5 here. Okay. Now in order to find out the determinant of adjoint of A, what do? We know the expression determinant of A raised to the power n minus 1 and is the order of the matrix. And since we can see that the matrix is 3 by 3 square matrix, so n you just put 3, in determinant of A you put 3, 5 raised 3 minus 1, 5 square is 25. This is your answer. If A is given this matrix and it is such that A inverse is equal to K into A, then find out the value of K. Since A is given, in order to actually work with A inverse, you have to tell precisely whether A inverse exists or not. For that, you have to find out the determinant of A. When you find out the determinant of A is what? It should not, determinant of A, if it is not equal to 0, then we can say it is showing that A inverse exists. So 2 into minus 2 minus 5 into 3. So minus 4 minus 15 is minus 19. This determinant of A is not equal to 0. So we can say A inverse exists. Okay. Now we know that we multiply A with A inverse, you get the identity matrix. If you multiply this A inverse equals KA, and then you multiply this A, see, A inverse into A is I, you know it, but we are going to deal with the question. So A inverse into K, let us multiply both sides by A, because A inverse you can replace it by K anytime. So I am replacing A inverse by K. So what do you have to do? You have to find out the A square. These two matrices you have to multiply because we have to find out A dot A. So when you multiply these two matrices, let me directly write the answer. I'm not going to do this because it's simple. 2 by 2 matrix multiplication you might have done a million times now. So K into this I'm just writing K. A square I'm writing as 19, 0, 0, 19, and this is equal to identity matrix equated with 1, 0, 0, 1, and then you can take 19 common from here because this matrix is simply a scalar matrix of 2 by 2 multiplied by 19. So you can take 19 outside and you can write this identity matrix 1, 0, 0, 1, and right hand side you have an identity matrix, so you can just cancel it out. Means if they are equal, it's simply you can cancel it out. K into 19 is equal to 1, so K will be equal to 1 by 19. So this is your K. K is 1 by 19 here. Let A be a square matrix such that A squared minus A plus I is equal to the null matrix 0. It is not 0, it is actually null matrix. Then write A inverse in terms of A. So all these type of questions we have done, and we have seen that the trick is to multiply the whole equation by A inverse. So the only thing is that you have to multiply both sides by inverse. So I'm multiplying this by A inverse. Here also A inverse into 0. Anything multiplied by null matrix is going to be a null matrix. So you can just write 0 here. It is not 0, remember. I'm just saying 0, but it is a null matrix. A inverse multiplied by A square. So A square is A dot A. You can just cancel these two out. It is basically identity matrix. A inverse into A is not cancelled. It is identity matrix. Again, A inverse into A is identity matrix plus A inverse into I. Okay. Now A inverse into I, if you multiply anything with identity matrix, you get the same matrix back. So A inverse I, take other things on the right hand side. Null matrix we don't deal. I minus AI. So A into I is again A, because anything multiplied by identity matrix you get the same matrix back. So what do you get? I minus A. This is your final answer. If C sub ij, this is called subscript Cij, is the cofactor of the element Aij of the matrix A, then write the value of A32, C32. This 32 is the subscript. So this cofactor and the value has to be multiplied. So in order to do that, let me tell you how to find out the cofactor, because the value is already there. So there are 3 rows and 3 columns here. In these 3 row and 3 column, this C32 means 3 is the row and 2 is the column. So which one of this? 5, this position. So third row and second column. So 5 is the A32, and we have to find out the C32. C32 is the cofactor. So let us take the cofactor first, and you already know in order to find out the cofactor, it's -1 to the power of I plus j. Then we leave the row and column intersecting at that value and take other value, that is 2 by 2. So 2, 6, 5 and 4 will be there. So what will be there? See, -1 to the power of 5 is negative. So 4 to the 8 minus 5, 6 is 30. 8 minus 30 is negative 22. Since it is already negative, negative of negative is positive, it will be 22. Now this is a C32. What is A32? It is already there. It is 5. So multiplication of A32 with C32 is equal to 5 multiplied by 22. So that is going to be 110. Find the inverse of the matrix. So there are various methods we have already discussed, and we have a shortcut method as well. And since the determinant is 1, the adjoint actually becomes equal to the A inverse, since the determinant of A is 1. Otherwise it would be different. So what do? We exchange the 5 and 3. So the diagonal element needs to be exchanged. So let us exchange this 5 and 3. So 5 is here, 3 is here, and then just change the sign of 7 and 2. So this is going to be 7, this is going to be 2. So this is your adjoint A as well as the A inverse. Why? Because the determinant of A is equal to 1. Or the next way is to find out the cofactor, find out the cofactor matrix, and then take the transpose, that is going to be the adjoint, and just divide it by the determinant of A. Okay. Find the inverse of the matrix. Same thing here, the determinant of A is actually 1 here. So what the best way is to exchange the cos, that is diagonal element. It won't change because they both are cos, and just change the sign of this negative sine theta and sine theta. So this will be sine theta, this will be negative sine theta. So this is your answer actually. Why it is coming? Because the determinant of A is actually 1 here. Cos square theta minus of minus sine square theta. So cos square theta plus sine square theta is 1. So this method which which demands that we try to find out the cofactors, this will be valid for all the n by n matrix. N by n square matrix. This is for 2 by 2. Just exchange the diagonal value and change the sign of the other values. Now if A is this one, write adjoint of A. So we need to do this. Let's do this because we have just skipped certain questions as we have been doing it a lot. Now let us do this properly. This is A11, this is A12. So first row, second column, first row, there are 2 rows, 2 columns, A11, A12, A21, A22. Okay. So cofactor matrix we are interested in. So wherever it is A11, so C11 will come like this, negative 1 to the power I plus j. Similarly C12, C21, C22, all will have a negative sign or plus or positive sign depending upon minus 1 to the power I plus j. And the value will be, what will be the value? I am writing it on the left hand side, the sign. Minus 1 to the power 1 plus 1, minus 1 to the power 1 plus 2. Here also 2 plus 1, negative 1 to the power 2 plus 2. So this wherever it is even, don't change the sign, it will be positive only. Wherever it is negative, it is going to be negative. Okay. Okay. Now C11, so take this A11, what will be there? 0. Now C12, so this will be 2. Just don't take that row and column, other value you have to take. C21 is 3, it was negative 3 basically, but since negative was already there, it was positive 3. C22, so this is C22, so 1 will take. Okay, this matrix, wherever we have this A, just replace it with C. So 0, minus 2, 3 and 1 will come. So this is a cofactor matrix. Now we have to change the rows to column, column to row. That is, we have to take the transpose. So we have changed the row to column, here also row to column. Okay, this is your adjoint. In order to find out the determinant, what we are going to do? Adjoint, inverse. A inverse is adjoint A divided by determinant of A. So we have 0 minus plus 6 is the determinant. You just divide it, it will be the inverse. If A is this, B is this, find adjoint of AB. So see, here is just to observe the question. Once you observe the question closely, you see that B is nothing but identity element. B is I. So when you multiply A with B, A can be any matrix, but B is here identity matrix. So once you multiply any matrix with the identity matrix, that matrix is going to come back, right? So A and multiplied by I, because B is nothing but I. So this is equivalent to the same matrix A. So essentially, adjoint of AB is nothing but adjoint of A. And you know how to do this adjoint of A? Just exchange A and D and change the signs of other values. So there is only one catch here in this question, that rather than you start multiplying A with B and try to find out A comes back, it's always A into B, I is A. Now A is this matrix, then find out the determinant of adjoint of A. So adjoint of A, it's very easy to find out the adjoint of A and then find out the determinant, right? We know already how to do the adjoint of A, exchange the diagonal values and change the sign of other value for 2 by 2 specifically. But we have a proper relationship here, which we have already done in the previous question. Adjoint of A, the determinant of adjoint A is nothing but determinant of A raised to the power n minus 1, where n is the order of the matrix. What is the order? 2. Okay. What is the determinant? 3 into minus 3 minus 2 into 1. So minus 9 minus 2 is negative 11 here. It's negative 11. So it is negative 11 raised to the power n minus 1. N is what? 2. 2 minus 1 is 1 only. So it is going to be negative 11. This is the way you can directly use it, or you can follow a proper method also. They both will be okay. Now write A inverse in terms of A, because A is already given and we can easily find out the adjoint of A, then we can find out the determinant of A, and in turn we can find out the A inverse. The determinant is 2 into minus 2 minus 5 into 3. So minus 4 minus 15, if you add, it is going to be negative 19. This is the determinant of A. So why we did this? Because we wanted to show that A is actually non-singular matrix. The determinant is not coming equal to 0. Therefore, it is invertible. This is an invertible matrix. Now, we'll try to find out the cofactor. Take the cofactor matrix, take the transpose, and that will be our adjoint A. Okay. So adjoint A, when it comes to A inverse, it is simply adjoint A divided by the determinant of A. That we need to follow. This is the actual say scenario. Okay. Now you have to write this A inverse in terms of A. So A has to come somewhere. So in order to find out this adjoint A is simply whether you can find out using the cofactor matrix. I'm doing it directly. You can use shortcut method also. So I'm just doing it directly. 2, so sign will not change, it will be minus 2. Then you take 3, it is 5, negative 5. Then you take this 5, it will be negative 3. And when you take this negative 2, it's going to be 2. Okay. So this is a cofactor matrix. And when you take the transpose, row and column, minus 2, minus 5, and this is minus 3 and 2. Okay. Now, where this is the adjoint. So keep it here. This is here, minus 2, minus 3, minus 5 and 2. So do you see that A and this matrix has something in similar? Yes. You take negative 1 outside, you get 2, 3, 5 and negative 2. So what is this matrix? This is your minus 1 and this is your A, right? But A inverse, since A inverse can only be completed when you divide it by determinant of A, It is negative 19, minus minus cancels, it is A by 19. So A inverse is nothing but A by 19. Write A inverse for A. So just take this, take the, you know how to find out the adjoint. Just exchange the value 2, 3 and then change the sign of 1 and 5. This is going to be your adjoint of A. And what is the determinant of A? 3 to the 6 minus 5. 5 into 1. You can do like that. Use elementary column operation C2 change to C2 plus 2C1. And there is one more question which is following, which is with respect to rows. Now this question is basically for finding the inverse by elementary row transformations or elementary column transformation. And always we write A equals IA or A equals A into I. Then we convert the right hand side I to actual A inverse, because we have to convert the left hand side A into I. Once you convert A into I, the right one automatically becomes A inverse, because A into inverse is equal to I. That is what we know. Okay. So what we do here is, this is A. We will convert I to A inverse, and in the process the A will be converted to I. So we assume this here. Left one will always be A. The right hand you can take any of this as I, any of these as A. Now notice, actually not A, it is actually A inverse. Because this particular snapshot is in between starting and final A inverse. So there are multiple row transformation or column transformation. This is one of the transformation. So let us change the column. So we'll not take this middle A, but the first and last will take, assuming it to be, it is going to be A inverse. So now C2 plus 2C1. So we have made the twice of and found out the twice of C1 and then added. And the C1 will not change. So I'm writing this C1 everywhere. This 3210 we are not changing. Now let me write this 1 minus 1. Now just multiply this with 2 first column and add it with the second column. So 5 and 4. Try 2 into 1 plus 0 and 2 into minus 2, 2 minus 2 plus 1, like that. Similarly here you have to do the same thing. Row 2 is row 2 plus row 1. So this whole is your row 1 total, and this whole is your row 2. But please remember, we are not going to change this I which I'm indicating. We're not going to do any operation on this. As I said, A into I is A. So on we need to leave. Okay, I into A is I. So let us assume that to be, because this process is somewhere in between. So only we will change one. This we are not going to change. So I'm just writing it. And row 2 plus row 1. So row 2 we are going to change. So row 1 you can just write directly. Means don't change it and just write it. So I'm writing row 2, 3, 8 minus 3, like that. And the row 2 has to be written as row 2 plus row 1. So 3 plus 4 is 7, 8 plus 9, 17, minus 3 minus 4 is negative 7. Okay. Okay, this is all about this exercise. Thank you so much. Take care of yourself.